So this is a lecture focusing on the second order step response. So any linear second order system falls in this category. And we're going to use the Laplace transform to help us understand what the step response looks like. So here's a transfer function for a second order response. This was, I'm using M, B, and K, so you can think of it as a mass spring damper system, but I easily could have had R, L, and C, or other physical domains that have second order systems that look like this. So our transfer function can be normalized. So that means I take one of those coefficients and say I want to make them 1. I often like the zeroth order term to be 1, and we will see later why that is. So this form you'll see here is fairly common, and then I'm going to introduce a generic version of that. So instead of actually having these physical parameters of mass, damping, and stiffness, we introduce new parameters, 3 new parameters. The steady state gain, that's in the numerator there, omega sub n, the natural frequency, and the Greek letter zeta, and that stands for the damping ratio. And so you can see that these forms are identical. In other words, m over k is 1 over the square root of the square of the natural frequency, and you can continue to see those connections. So here's these three parameters. So we say we've parametrized the second order system to these 3 parameters. All linear second order systems can be parametrized in this way. The other part of this is that if you have a system that is behaving like a second order system, then you can look at its step response. In other words, hit it with a step input and record its response. You can then extract these 3 parameters and learn something about this system. Okay, so let's look at this. Here's the characteristic equation. So we took the denominator of the second order system of that transfer function, set it equal to 1. And so we have a quadratic in S, right? S squared, S, and 1. And as we remember from quadratics, there's 3 possible outcomes of this. You could have 2 distinct roots that are both real. I'll call this P1 and P2. You could have a perfect square in which there is only a single root that's repeated. Or you could have complex roots. And if the coefficients are all real, then these roots will be a complex conjugate pair. So if you want to think about how we would factor that polynomial, or the characteristic equation, in that first case, you get S plus P1 times S plus P2. So those P1 and P2 or minus P1 and minus P2 are distinct roots. And that is what we call the overdamped case. And it turns out that if that zeta parameter, the damping ratio, is greater than 1, that's what you'll have. We call it overdamped. If zeta is exactly equal to 1, then it's critically damped, and that's that repeated root of P1 minus P1. And then if it's underdamped, you get these complex conjugate pairs. And I'm putting them in this form. They actually will fall in this form. In other words, the real part will be zeta times omega n. The complex part will be omega sub d, which we now introduce yet another parameter. It's just based on 2 of them. It's the damped natural frequency, and we'll see where this shows up at a later time. So here's the transfer function, and we hit it with a step input. So we kind of we bring that input u and put it over on the right hand side. So the Laplace transform of y, our output, is equal to the transfer function times the Laplace transform of the input u. If u is the unit step, which is what we're looking for, then u of s is equal to 1 over s. So the step response, the Laplace transform of the step response looks like this. And so all we have to do, and I know that's not a trivial thing, is take the inverse Laplace of this thing, right? So we saw briefly in class, and there's plenty of books and plenty of videos that describe this. We can do what's called the partial fraction expansion to break this down into parts and look it up in tables. Or if you're lucky, you can find the form you're really looking for right in the table. This particular form isn't in the table in the back of the book. It's a pretty abbreviated table, so I didn't have to look very far in the literature to find this table. It's at from Swarthmore University in Pennsylvania. It's a very nice Laplace transform table. I put a link to it in Blackboard. You can find it there. But it's about a page and a half, and this is down towards the bottom of the second page. There's these three forms, and here's one we're looking for. We have a constant term in the numerator. We have a quadratic multiplied times an s, right? Quadratic and s multiplied times s, and there's the output of the, and this is what the inverse Laplace looks like. But before we jump to that, we have to align up our problem with the table entry, right? Make sure they're of exactly the same form. So this is what we have, and this is what they have, right? And so part of the problem here is that is that the one in the numerator, right? So I have it normalized differently. Their normalization is that the coefficient of the s squared term is 1, and I have the normalization as the s to the 0 term is 1. So what we have to do is just multiply the top and bottom by omega n squared, and we'll get the same form. So when we multiply the top and bottom by omega n squared, we get this form at the top. Now it looks an awful lot like the form in the table, with only two differences. One is KSS, but that's a constant term. We know it's a linear transform, so I can pull that out, put it out in front of the whole thing. And what they called, they're referring to omega sub 0 or omega naught. We're calling omega n natural frequency, and those are the only two differences we have to make. And so we can go back to the table and now focus on the inverse Laplace transform, which is a function of t, which is the response. So let's take a closer look at that. That step response now is KSS times 1 minus this another coefficient with zeta in it times an exponential times the sine of omega dt plus phi. And phi is a phase shift, and it's an easy function, arc cosine of zeta, the damping ratio. And recall omega sub d was the damped natural frequency, which we saw earlier on. So this is a really classic response. This is seen a lot in physics and in control systems. It's a really big part of control systems. So it's worth taking some time to kind of absorb this and kind of pull this in and really understand it. Two main components. It's a decaying exponential, because there's that negative term in the exponent, and a sinusoid. So you can see that you have an oscillating solution, because there's a sinusoid that's getting smaller over time, right? So this decaying oscillation is a classic response. And I want to take a look at this a little further. So remember, when we factored this in terms of zeta and omega n, factored the characteristic equation, we said the roots were of the form minus zeta omega n plus or minus j omega d, right? And I wanted to point that out because the real part of that root shows up as the exponential, just like it does with any of our real roots, right? If our root was minus p, then our solution has an e to the minus pt in it, right? The imaginary part ends up being the frequency of oscillation, right? So omega sub d, the damped natural frequency, is actually the frequency of oscillation. This is worth repeating, because when you see the oscillation in the response, that frequency is not the natural frequency, unless zeta is equal to 0, in which case they're the same. An undamped system has just the natural frequency, right? But if there's any damping at all, the actual frequency will be somewhat slower than the natural frequency. So I wrote a script in MATLAB to recreate the figure that's in the textbook. I think it's 4.5, showing a family of second order step responses normalized in time. So that's not seconds along the bottom axis, that's omega n times time. So depending on omega n, you can kind of dilate it any way you want. And it is for a steady state gain of 1. Okay, so that's why that all settles out to 1. And I did this for a family of zetas. And you see the blue line is zeta equal to 0.1, and you see a very high overshoot and a lot of oscillation, and down at the light blue line, it's zeta 0.7, you get just a bit of overshoot, and no oscillation. And at zeta equals 1, which is the critically damped case, you get no overshoot at all. So you can look at this and compare this to other responses, or you can recreate any response you want. Sketch any response you want. So a few things to pay attention to is what do I mean by percent overshoot? Well, it's the percent above the steady state line. It is. So in this case, the steady state line is 1. We get about 0.72 maybe. So this zeta equals 0.1 has about a 72% overshoot. I want to point out these little sharp corners in this response. That's an artifact of how MATLAB calculated it. In reality, mathematically, it should be just a smooth sinusoidal sort of response here. The damped natural frequency determines the period between two adjacent peaks from here to here. That period of time is the damped period. 2 pi over that is the damped natural frequency. And so you can pull out zeta from this. You can pull out the damped natural frequency and the steady state gain by looking at where your response settles out, and you've completely determined the response. One thing I want to point out about second order step responses, implicit, right, and assumed with any of these step responses is zero initial conditions. So we saw in the exponential of the step response of a first order system, we saw a slope, a non-zero slope at time t equal to 0. A second order response has two initial conditions, one of which is the slope at time t equal to 0. And so, like the first order response, we start at the output equal to 0, but unlike a first order response, the slope is also 0. So if you zoom in on all these, if you were to ask MATLAB to say, well, just give me the few first milliseconds of it, you see that the slope starts off flat and then starts curving up. It's a little hard to see here, but you can it's certainly true. We'll see that. So that's it in a nutshell. That should give you enough information to do those two second order problems in the problem set, and that's it.